Welcome back to the beginning of Chapter 4. In this chapter, we're not going to learn how to take new derivatives. We've already covered that. There really won't be any new derivatives that we'll learn for pretty much the rest of the year. In Chapter 4, we're going to learn how to apply these derivatives, some of the applications of them, what do they mean, how do we use them, lots of stuff like that. We've touched on some of these topics a little bit in the past couple chapters, but we're going to really focus on these now. And so, this first section, we're going to look at what derivatives tell us. Same thing with the second section, actually. The first section, we're going to look at the topic from an equation perspective. The second section, we're going to look at the same thing, but looking at graphs and tables and seeing how that works. So, what do derivatives tell us? First of all, before we get to a derivative, what does the function tell us? The function, we can find zeros, and there's a lot of applications of those zeros. And that's what we've been really working on for the past, 3 years. Finding zeros of functions, what does it mean, things like that. So we won't focus too much on that in calculus. The function will also give us the value, the y value. Y value is very generic. It's the vertical axis value, the function value. It gives us that, and the function is the only place where we can get that. We'll be looking at maximums and minimums. The derivatives and second derivatives will tell us how to find where they are to tell us the x value. But to find the actual function value, what is the maximum or minimum, we do have to plug it into the original function. We can't, the derivatives and second derivatives won't give us that. So those are two very important things the functions give us. The next thing we're going to look at is the derivative. The derivative is going to give us what are called critical points. That's when the derivative either equals 0 or does not exist. We won't get too many does not exists in this section because we're starting with equations. The does not exist part would come from piecewise functions. It could also come from if we have absolute values or something. We'll get those a lot more looking at tables and graphs in the next section. But critical points are when either the derivative equals 0 or does not exist. And what that will tell us is maximums and minimums. Maxima and minima happen at critical points. And so we're able to find those. Now, one of the biggest mistakes is someone gets a derivative equals 0, and so obviously there's a maximum or minimum there. Not necessarily true. A maximum or minimum happens when the slope, which would be the derivative, changes from either positive to negative to get a maximum, or negative to positive to get a minimum. The slope changes signs. It's possible that the slope could be positive, go to 0, and then continue to be positive. For example, the x cubed function. Slope is positive, 0 goes to positive. There is a critical point right there. That is not a maximum or a minimum. It does not guarantee it'll be a maximum or minimum, just that that's where it could be. We still always have to check a table or a number line where you'd put the critical points and then see what the derivative is in each of the different intervals, whether it's positive or negative. And then it's only when it changes signs that happens. And then with the maximum minimum, that gives local maximum and minimum. We're also going to be looking at extreme maximum minimum or absolute maximum or minimum. generally on an interval, and we'll see what happens there, but that's either when the derivative equals 0 or the endpoints of the interval. And we'll see a problem where we do all this stuff. And the derivative also tells us whether or not the function is increasing or decreasing. When the derivative is positive, the function is increasing. When the derivative is negative, the function is decreasing. And then we have the second derivative. The second derivative gives us points of inflection. The points of inflection are the critical points of the second derivative, when it equals 0 or does not exist. And now a point of, or that's when it could happen, but really it's when the second derivative changes from positive to negative or negative to positive. A point of inflection is when the concavity of the function changes. Concavity is it's the curvature of the function. We have concave down, which means it's curving down. We have concave up, which means it's curving up. So down, up. Concave up could hold water, although that's concave up, not going to hold water, but concave down definitely can't. So the second derivative gives us points of inflection, which would be when it changes from concave up to concave down, or vice versa. So if you're drawing right here is where it changes from curving downward to curving upward. Running your pencil along it, you can kind of feel the change, but we're going to figure out where those points are. And it can also tell us the concavities I just was mentioning. Up is when the second derivative is positive. Down is when the second derivative is negative. And so we'll be able to see those. So what does a problem look like? Problem looks kind of like this. It gives us an equation. We'll have to find the critical points, local extrema, the extreme values, where it's increasing or decreasing, then the x-coordinates of the point of inflection, and where it's either concave up or concave down. So it takes us through all of those different pieces that we were looking at, which is fine because a lot of them overlap quite a bit. So to do this, looking for the critical points, we're going to look to see where the function or where the derivative is 0 or undefined. Being that the function's a polynomial, the derivative is not going to be undefined. So we just need to look to see when the derivative is 0. So first we need to find the derivative. So it's going to be 3x squared minus 12x minus 15. Now we need to set it equal to 0. And while doing so, I'm going to factor out that 3. X squared minus 4x minus 5. 3. X minus 5, x plus 1. So it's when x equals 5 or negative 1. So the critical points, okay, the critical points are when x equals 5 and negative 1. Find the local extrema. It's probably going to happen at those points. We need to know if it's minimum or maximum or if it happens at all. So for B, we're going to make a table or a number line. We have x, we have f prime of x, we have the derivative, and we're just looking to see if the derivative is positive or negative. So let's put our numbers on here, negative 1 and 5. And for these, I see this all the time. Make sure you put the numbers in the right order. Negative 1 is smaller, it goes on the left. I see people put numbers in all sorts of orders. When we have 3 numbers, not even putting the middle number in between them, that will cause problems. Big, big problems when there really should not be problems. Anyway, let's plug in some numbers. And when we plug them in, we're going to plug them into that equation because we don't really actually care what the numbers are. We just want to know if it's positive or negative. So if we have a negative number, like say -3, well, 3 is always going to be positive. That's not going to change the sign. Plug in -3, that's going to be a negative number times a negative number. A negative number times a negative number is a positive number. At -1, it's 0, just as like at 5, it's 0. Let's plug in a number in the middle, like 0. Let's see, positive, negative, and positive, because 3 is always positive. 0 minus 5 is negative. 0 plus 1 is positive. Positive times a negative is negative. And then plug in a number bigger than 5, like 10. Positive, 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 multiply them together, you get positive. And so we look for the change of signs. There's going to be a change in sign here and a change in sign here. So the first one, it's going from positive to negative. The derivative's going up, 0, then down. That's a maximum. So a maximum at x equals -1. And then over here it's going negative, 0, positive. That's going to be a minimum. Minimum at x equals 5. That would be our local extrema. And then for part C, it says find the extreme values of the function on the interval -2, 6. So for the extreme values, that's just like what is going to be the biggest thing on the interval, what's the smallest thing on the interval. It's either going to happen at one of these values or at the end point. So we just need to plug those in to the function itself. So we're going to have f of -2, because -2 is an endpoint. That's going to equal something. F of -1. F of 5. And f of 6. So we just need to plug these into the equation. If we plug in -2, -2 cubed is -8, -2 squared is 4, times -6 is -24, plus 30 plus 2, that gets 0. Plug in -1, that's -1, minus 6, plus 15, plus 2, that's going to give us 10. Plug in 5. When we plug in 5, we get 125 minus 6 times 25 minus 15 times 5 plus 2. You get -98. And plug in 6. 6 cubed is 216 minus 6 times 6 squared. Well, 6 cubed minus 6 times 6 squared is 0. So we have -15 times 6 plus 2 is -88. So now we're looking for the extreme values. The biggest number is at -1. So the max is 10 when x equals -1. The minimum, smallest number there is 98. So the minimum is -98 when x equals 5. So that's part C. So as we just plugged in those values, there's no calculus involved in that question. Part D, where on the interval is the function increasing? I want to do this one before we move over because we already have this work done. Because we know it's increasing there and there. So we'll put it underneath the problem. D, increasing on. So from the beginning of the interval to -1, so that would be -2 to -1, and 5 to the end of the interval, 5 to 6. So a couple things to notice here. The increasing part is just when it's positive. The derivative's positive. We got that. So it's increasing from -2 to -1, including when x equals -2, but not including when x equals -1. And then same thing, it doesn't include 5, but it does include 6, because at the endpoints, it's still increasing. At -1 and 5, it is not increasing. The derivative equals 0. So we wouldn't want a closed interval on that end. So that would be, where is it increasing? Next question, what are the x-coordinates of all the points? So for the x-coordinates, or of all the points of inflection, for that we need the second derivative. So our first derivative, again, I know it just got erased, but it was easy enough to find. 3x squared minus 12x minus 15. So then the second derivative will be 6x minus 12. Points of inflection, we need it equal to 0 because it will be defined, so we don't have to worry about that. But 0 equals 6x minus 12. Add the 12, divide by 6. X equals 2 is the point of inflection. So that's E. And then F, what values of X is the graph of F concave up? Well, actually, I guess before point of inflection, we would have to do the same idea. We have 2, 0. This is F double prime of X. X, plug in a point that's smaller, plug in a point that's bigger. All right, so if we have, plug it into here, if we have 6 times 0 is 0 minus 12, that's negative. Plug in 5, 6 times 5 is 30 minus 12 is positive. So yes, it is a point of inflection. And then part F we already have done. For what values of X is the graph of F concave up. Well, it's concave up when that's positive. So when X is bigger than 2. Concave up when X is greater than 2. So that's what we're doing this section. It's just a bunch of that same problems because those are the questions that are going to be asked. Um, we'll be figuring out how to apply these in different ways later on, but this is just the idea of, hey, this is what this means, this is what this means, this is what this means, this is how you find this, this is how you find this, this is how you find this. So keep working problems, keep asking questions, and as always, happy mathing.